Welcome to lab number 3. In today's lab, we're going to investigate Poiseuille's law from chapter 3 and learn something about pressure. Poiseuille talks about the flow under pressure of flow through a tube. And we're going to measure the flow for 3 different tubes today. But the pump we're going to use to cause the pressure is not a normal pressure pump or even a vacuum pump like we used last week, or the compliance pump like the heart operates. Rather, we're going to use the pressure caused by a column of water under gravity. Now you look at this reservoir of water up here and you say, well, how does this shape affect that pressure? It's a triangular shape, odd shape there. How does that affect the pressure causing the flow through the tubes? Well, to answer that, let's turn to our good friend Blaise Pascal and see what he has to say about the effect of the shape of the tube. Well, here I have an apparatus that will help us to determine what the pressure is at the bottom of a volume of water under the acceleration of gravity. I have a carboy here filled with water from this level at the bottom up to the top, and I have a pressure sensor that's located at the bottom that will measure the pressure at the bottom of this volume of water. Let's use some equations to see if we can predict what the pressure gauge will read on this gauge when I turn it on. So let's see what the equations tell us should be the pressure at the bottom of this container full of water. Here is a sketch of that container with its dimensions. The height of the container that has the water in it is 33 centimeters from the bottom up to this point in the container. The cross-sectional area in the horizontal direction is area A sub A is 580 centimeters squared. So let's calculate first the force, total force at the bottom of that container at F sub A, and then its pressure later. The force, F sub A, is given by Newton's second law, mass times acceleration. In this case, the acceleration is the acceleration of gravity. Notice that the mass of that water is just its density times the volume inside that container times the acceleration of gravity. But the volume is the area, A sub A, times the height, H sub A. If we put in numbers, the density of water we know is 1,000 kilograms per meter cubed. Notice we're working in the SI system. The area A sub A is 580 centimeters squared, which is 0.058 meters squared. The height was 33 centimeters, which is 0.33 meters. And then we know the acceleration of gravity is 9.8 meters per second squared. When we put that into our calculator, we get 188 newtons is the force at the bottom of that container. But now we're interested in pressure. Pressure, as you know, is force divided by area. So the pressure at the bottom of the container, which is sensed by this pressure sensor, is F sub A divided by A sub A, by the area A sub A. We've just calculated that the force is 188 newtons. We divide by 0.058 meters squared. A newton per meter squared is a pascal. And what we get is 3,200 pascal, or 3.2 kilopascal. Let's see if the meter actually validates that number. And as you can see, the gauge, which is reading in kilopascal, is indeed reading about 3.2 kilopascal. Next, I'm going to fill this very narrow tube, which is connected to the top of this carboy container of water, with water up to this point right there. Let's see if we can use our intuition to tell us how much we think the pressure at the bottom of the container is going to increase because of the volume in this very narrow tube up to this point. So using our intuition, let's see if we can make a very rough estimate of how much the pressure at the bottom of this container is going to increase when we fill this very tiny narrow tube here with water up to that point there. Notice that the cross-sectional area of that tube is only 2 centimeters squared. That's about 1/300th the area of the main container down here at the bottom. So even though it has twice the height, the volume of the water in that tube is going to be less than 1/100th the volume of the water in the bottom of the container. We previously found that the pressure due to the water in the bottom of the container, in the bottom container, is 3.2 kilopascal. So we guessed that maybe when we fill that up, it has such a small volume that it's going to add just a few pascal to the 3,200 pascal. Well, let's try it. Let's see what happens. I'm now going to fill this narrow tube that's on top of this container of water connected to it with water up to this mark here. And we've anticipated that it's not going to add very many pascal to the more than 3,000 pascal that we have on this pressure meter. Let's see what happens when I fill that small tube with water up to this top mark. Standing on a step stool, which I'll call Pascal's ladder. I'm filling that tube with water now, up towards the top. Look at that pressure gauge. Wow. It's going way, way high. Almost higher, almost to the maximum, higher than 9 kilopascal. Wow. Can we explain that by the equations? By physics? Let's look at the equations. So let's see if equations can explain that remarkable result. We filled the tube up with water up to a height of 66 centimeters. Let's find the pressure at the bottom of that tube, and then we can add that to the pressure of the bottom container to find the total pressure detected by the pressure sensor. Well, to find the pressure at the bottom of the tube, we'll call that P sub B. You take the force at the bottom of that narrow tube and divide by the area of that tube. Well, we know from previous calculations that the force at the bottom of a column of water, force, is density times area times height times the acceleration of gravity. Let's immediately divide that force by the area A sub B. Notice that the areas cancel out, and that's a key to this phenomenon, leaving us with the equation that the pressure at the bottom of a column of water is the density times the height times the acceleration of gravity. You're going to use that expression in today's lab to calculate the pressure that's going to drive the flow through the various tubes that we're going to measure today. Putting in values for each of those for this narrow tube, the area of the tube cancels out, and we're just left with density times height times acceleration of gravity. And on the calculator, that gives us 6.4 kilopascal, twice as much as we had earlier for pressure. Why? Because it's twice as high. It's 66 centimeters rather than 33 centimeters. We add those two pressures together to get the total pressure at the bottom of the container as measured by the pressure sensor, and we see that that's 9.6 kilopascal, very close to what the pressure sensor measured. That is a demonstration of Pascal's principle, because Pascal's principle says that the pressure at the bottom of a column of water does not depend upon the area or even the shape of the tube. So what we've just demonstrated is something that a French mathematician, physicist, and philosopher, Blaise Pascal, demonstrated back in about 1650. And that is, he took a very sturdy rain barrel at his farm and put a very tall but narrow tube pipe on top of it, got up on his ladder, which is called Pascal's ladder now, and he poured water into that tube. Notice how tall that tube is. Notice the height of that water. Well, the pressure at the bottom of that tube was enough to burst this very, very sturdy rain barrel apart, to the amazement of his neighbors. That's called Pascal's ladder. And so once again, Pascal's principle is that the pressure at the bottom of a column of water does not depend upon the size of the tube or even the shape of the tube. As you can see here in this demonstration, Notice that the pressure at the bottom of these various tubes is independent of the size of the tube or the shape of the tube. That is Pascal's principle. Oh, incidentally, look up Pascal's wager if you want to learn a little bit about his philosophy. And then just finally, to demonstrate how this might apply to everyday life today, here's a diagram of a dam holding back a lake of water. Let's say it's Lake Powell. The pressure at the bottom of the dam does not depend upon the size of the lake. It doesn't depend upon how many acres of water Lake Powell holds. It only depends upon the height of the water from the top of the water down to the bottom of the dam. Now, let's use those calculations to apply it to today's lab. So Pascal has taught us that the shape of the reservoir here does not have any effect on the pressure. It's only determined by the vertical height against gravity from the top of the water to where it comes out the bottom of the tube here. Let me demonstrate that for you. Let me start the water flowing by turning on this valve. And you notice that the water is flowing when it's down here at this level. But as I go up higher and higher, the water flow diminishes until I get to the height of the reservoir and the water flow stops because there's no net vertical height anymore. And it really is vertical height, not horizontal, because let me show you the flow of this water out of the tube. As I move in a horizontal plane, gravity is the same along that horizontal plane. It's only the vertical height against the vertical gravity that is important here. Now let's make some measurements that will allow us to calculate the fluid resistance for tube number 1 here. But before we do, please make a sketch of tube number 1 in the appropriate spot on the worksheet. It will look something like mine, but make it your own. And then let's measure the dimensions of tube number 1. The length is 1.0 meters, 1.0 meters. And the inner diameter we can determine using the same idea we had from last lab. We'll insert a blunt end of a drill bit and find that the inside diameter is 1/8 of an inch, 1/8 of an inch. Please mark those down on the worksheet. Now, to determine the fluid resistance of this tube, we're going to use the simplified equation for Poiseuille's law, namely equation 3.7. And to do that, we're going to have to first measure the flow rate for a given pressure. The flow rate we can determine by turning this valve on and then using a stopwatch determining how much time it takes to collect, let's say, 100 milliliters of water in this beaker. Let's do that now. Turning this on, starting the stopwatch, and it's filling quite rapidly. There's 50 milliliters, getting closer and closer. Right there is 100 milliliters, and that took 17.10 seconds, 17.10 seconds. Please mark that down as the time on your worksheet, T. And then to find delta P, you have an equation that relates the pressure to the height of the water column. And that height is the difference between where it came out of the tube, which is pretty much this tabletop, to the height of the water at the top. And I measure that as 55.5 centimeters. 55.5 centimeters. Please use that to find delta P. And then using equation 3.7, calculate the fluid resistance for this tube in clinical units. The clinical units would be liters, seconds, and millimeters of mercury. Now let's turn to tube number 2. Tube number 2 is a little different. It's composed of one length of a single tube. It's actually the same material as tube number 1 with the same inside diameter, but a different length than tube number 1. And then it bifurcates into 2 parallel branches here. Again, the same tube material as tube number 1. They each have the same length, but it's different than tube number 1. I'd like you to make a sketch of this tube number 2 on your worksheet, and the sketch will look maybe something like this. Notice that I have labeled the three segments of the tube with different symbols because we're going to combine them differently. The length of the single element of this tube number 2 is 75 centimeters exactly. The length of each of the two branches is 50 centimeters exactly. Please mark those down on your worksheet. And then, based upon what we just measured a few minutes ago for tube number 1, based upon that value, estimate, before we make the measurement, the resistance of tube number 2 based upon that value of what we measured for R1, and then equations 313 and 320 in the textbook. Please make that estimate in this space here and write it down in this location before we actually make the measurements. Now let's make some measurements of the fluid resistance of tube number 2. I've placed the two branches of the outlet of tube number 2 in the beaker, and using the stopwatch, I'll measure how long it takes to collect 100 milliliters in the beaker. $50. Getting closer. 16.75 seconds. 16.75. Please mark that down on your worksheet. And from that, make a measurement of the measured resistance for tube number 2 in clinical units. And now that you have that and the estimated value, please calculate the percentage difference between what we estimated and what we measured using this standard formula for percentage difference, and put that down on the worksheet. Now let's turn to page 3 of the worksheets and tube 3. Tube number 3 is different than the other two tubes in that it's a lot longer and it has a much smaller inside diameter than the other tubes. Please make a sketch of this similar to the one I've shown here on your worksheet, and let's make some measurements of its dimensions. The length of tube number 3 is 1.5 meters long, 1.5 meters long, and the inside diameter, using those blunt end of the drill bits like we did before, is 1/16 of an inch. 1/16 of an inch. Please mark those down on your sketch. Now let's make a measurement of the fluid resistance, similar to what we did before. But I can anticipate something. Since this is longer than the previous tubes, but especially since its inside diameter is much smaller, it's going to take a lot longer to make this measurement, because the fluid resistance I can anticipate of this tube is going to be a lot higher than the previous tubes. So, to sort of accommodate for that so that we don't have to spend a long time making this measurement, I'm going to increase the pressure. How do I increase the pressure? Well, I'm not going to raise the height here, but I am going to drop this beaker, that collection beaker, down lower, down to the floor, so that I can increase the vertical height of that column of water. And let's make the measurement with the beaker on the floor. Now, to get the total height of the new water column for measurement of R3, we're going to have to add the height of the water to the top of the table, which is 55.5 centimeters, to the height of the table off of the floor, and that is 95.0 centimeters. Add those two together to get the total height of the water column for the measurement of R3. Starting the flow of water. It is flowing a lot slower. One minute, 22 seconds, and 7/10. 1 minute, 22.7 seconds. Please mark that down, and then use that to calculate the fluid resistance of tube number 3 in clinical units. But we're going to need different units for the next step. So convert those clinical units of resistance to SI units of resistance and mark that down on the appropriate spot on the worksheet. Everything we've done up until now has used the simplified version of Poiseuille's law, equation 3.7. Oh, and incidentally, we're going to use that simplified version a lot in the major project later. But now, let's look at the more complicated expression, theoretical expression for R3, namely equation 3.6 in the textbook. And based upon the dimensions of tube 3 and the viscosity of water that you can look up in the appendix like we did before, please calculate R3 theoretical in this expression right here from equation 3.6. And it'll be in SI units, so write that value in this line right here. And then pause this video and come back for the final calculation. To finish up, please calculate the percent difference between the measured value for R3 that we did earlier and the theoretical value for R3 that you've just completed. Use the same equation for percentage difference that we've used before. That percentage difference, it's not going to be really close to each other, but the percentage difference should be less than 30%. If your percentage difference is greater than 30%, you've either made a mistake in the conversion factor from clinical units to SI units done earlier, or you've made an error in the calculation of R3 from equation 3.6. Please correct those things to get your percentage difference less than 30% before we go on. And then finally, right here at the bottom of the last sheet, one possible reason why you think that the measured value of R3 and the theoretical value didn't agree. Just write down what you think might be a possible reason. Well, I hope you enjoyed Lab 3, and I look forward to seeing you in Lab 4 next week.